We are ready to start. So welcome everybody. Welcome family and friends and co-workers and collaborators. You in the audience and also people that are following this event online. So I would like to welcome you all to this PhD defense of Turið Poulsen, which is based on a thesis entitled Analysis and Modeling of Wind Energy Resources in the Faroe Islands. So it's a very important topic both for the Faroe Islands but also on the global stage. The PhD project has been done at the University of Faroe Islands with Hans-Georg Beyer as main supervisor, and with the contribution from Barr Niklasen and Gregor Diedel as co-supervisors. I'm going also to warmly welcome our international guests, so the opponents, which are Professor Infield from the University of Strathclyde in Glasgow, Scotland, and Dr. Estanquero from Laboratory Nacional de Energética Ecológica from Lisbon, Portugal. I don't know how the Portuguese was, Anna, but you can do it better than that. And then I would like to welcome also Cholmar Hatun, Associate Professor at the University of the Faroe Islands, who is the chair of the assessment committee. So the program of the day is that after my introduction, Cholmar Hatun as chair of the assessment committee will give short remarks on the thesis work done by Turið Poulsen. And then we will have the main event with Turið Poulsen having her presentation of her scientific work. And after that, we will have the two opponents, starting with David, and followed by a break, and then Anna. So this is the program for the day, and I wish you all a successful event, and I will give the floor to Cholmar.
Is this on? Yeah, there we go. Yes, I'm Cholmar, and I'll read up from our recommendation. The thesis presents a detailed analysis of wind variability in the Faroe Islands. Wind variability is an important topic as it impacts on the challenges of wind integration into power systems. This is particularly difficult for small power systems such as in the Faroes, where geographical diversity is limited and the topography is complex. Our main goal in this work is to generate a wind farm portfolio which optimizes the combinations of high power output and low power fluctuations. The approach for obtaining this important goal is based on standard power spectral methods applied to observational wind speed and wind power time series, together with output from numerical models. The thesis consists of 3 papers, 2 published in international journals and 1 submitted. Turið Poulsen is the lead author on all 3 papers. This material is described in a synthesis which consists of 7 chapters. Some positive points. The overall aim of this thesis is both relevant and important, as you heard. The thesis is well written and the presentation is clear and focused. Data and methods applied are adequate for a PhD dissertation, and these are thoroughly handled. The application of standard analysis techniques, it's novel. The conclusions, the quality of this work and its presentation is consistent with the international standard expected for a PhD. We, therefore, find that the dissertation fulfills the requirements for the award of the PhD degree, and it is thus recommended for defense at the University of the Faroe Islands. And then Turið, I welcome you to the podium.
My Ph.d. project analyzes a modeling of the wind resource in the Faroe Islands. The work has been compiled in this dissertation here, which includes or is based upon a few posters as well as 3 journal articles, as Tolmar also said, 2 are published and 1 is now it's in review. Today's talk is going to be the following outline. I'm going to start with an introduction and then follow a description of the data and some methods that are applied. And after that, I'm going to talk about the results of Article 1 and 2 and 3. I'm not going to mention all of the results because of the time limit. However, you're welcome to read the dissertation and the articles, which are open source. And then I'm going to end up with a summary and conclusion. So the general aim is to characterize the wind resource in the Faroe Islands. The climate of the Faroe Islands is very windy. To the right, you can see windrows from measurements at a met mast close to Tórshavn, where the average wind speed is 10 meters per second. And high wind speeds leads to good potential for wind energy production. There are a lot of benefits with wind energy. It is environmentally friendly, it is cheap, and it's also in the Faroe Islands, it's abundant. The politician goal of the Faroe Islands, as well as the local power company of the Faroe Islands, are aiming at producing all electricity from renewable energy resources by the year 2030. And because we have so much wind, this also includes manifold of increasing the wind power capacity in the Faroe Islands. But wind also has its downside. It's a variable power source. If you have wind, you can have wind energy production. However, if you do not have wind, there's simply no wind energy production. And it fluctuates also at different time periods. Here you have a graph with 1 year running mean of wind speed of the same data presented before. And you can see some, for the duration of 1 year, the wind speed can be as high as 11 meters per second, while other periods it can be approximately 9.3. So it fluctuates annually. It also fluctuates seasonally. So we have, in the Faroe Islands, we have higher or more wind during winter and compared to summer. We also have wind in summer, but less than winter. Wind also varies over days. Some days you have more wind than others, also over hours, etc., etc. And once wind varies, other power sources need to counter the fluctuation of the wind resource, which is why it's important to investigate how, and which is also the focus of the dissertation, to investigate the fluctuations of the wind resource. The research objectives of the 3 articles can be put in these 3 bullet points. The first article examines the general characteristics of the wind in the Faroe Islands. And the research objective of the second article is to validate wind simulations, which are generated with the software Weather Research and Forecast. I can mention here that the simulations were made by Killer and made available to me through the power company of SIV. And the third objective, which is the objective of the third article also, uses these WRF data, WRF simulations, to optimize wind farms' portfolio for the Faroe Islands in order to reduce the wind power fluctuations. So a little bit of introduction here. The Faroe Islands is located in the northeast of Atlantic Ocean. It's far from neighboring countries, which means that we have our own power grid. small power grid. And the current power production is the power source of the power in the Faroe Islands is wind, hydro, and oil. And then there's a little bit of solar, biogas, and tidal. In 2021, 13% of the electrical power was produced from wind, 24% from hydro, and 62% from oil. Currently, we have 4 wind farms in the Faroe Islands, 25 megawatts. However, there are 3 projects in process. One, the 18 megawatt, is very far in the process. It's being installed, and it's expected to be connected to the grid very soon, or running on the grid. However, by 2030, it is estimated in order to reach the goal of running entirely on renewable energy resources, wind power is expected to increase to 170 megawatt by 2030. The data I have used in the analysis is a mixture of measurements and the WRF wind speed simulations. So the measurements are wind farm power data from 3 of the wind farms which were operating at the time of the analysis. And the wind speed data are from 5 met masts, 2 in Aia, 1 in Husehea, and 2 in Suðuroy, while the WRF data are available everywhere. Once I analyze the power, I either use power measurements or I use power data that it has been converted from wind speed measurement using this power curve of a turbine, as there is a link between power production and wind speed. I'm only going to mention 2 of the methods that I have used in the dissertation, which I think is very important because I use them over and over. The other methods that are used will be explained along the way. The first one is the autospectra. An autospectra explains how a time series fluctuates with respect to frequency or time period. So the higher the spectral amplitudes are, the more fluctuations the more the time series fluctuates at that time or frequency. And the second method I like to introduce before I go to the results is a term called coherency. I've shown 2 examples here to illustrate. They are made up examples and very exaggerated examples. So if you have, for example, 4 turbines standing very close to each other, you can expect that the time series co-vary. So once you have high power production at one turbine, you expect it to be high at the other. While if you have distributed wind turbines, you can expect that the power production might be more independent, have a lower coherency with respect to each other. And if you add the power production from all turbines, you get higher fluctuations if you have high coherency between the time series, and lower total fluctuations if you have low coherency between the time series. This leads us to the square coherence function, which is used throughout today's talk. The higher the coherence values are, the more 2 time series fluctuates with respect to each other at that respective frequency. So I will start by going through some of the results of the first article, spectral characteristic and spatial smoothing of the power, a case study of the Faroe Islands. The goal is to examine the temporal and spatial fluctuation of the power production. And the results of this first articles are based on measurements at 6 different sites in the Faroe Islands. So first you can see at the autospectra for all these 6 time series. You can see that there's a peak around 3 days, which is consistent with the fact that we have low pressure systems traveling east in the north and mid and high latitudes. And you can also see that there is no significant peak for frequency one day at the period of 1 day, which means that we don't have this daily phenomena, which you can see at other locations where the land is heated and cooled down, so you get this daily effect. And it's speculated it's because we are in the middle of the ocean, which reduces the daily fluctuations of the, or it doesn't reduce, it doesn't, this phenomena isn't here. And the second plot I like to show from the first article is the square coherence function between all possible side pairs. You can see that there's a high coherence for very close wind farms, which have the color blue, while the more distant wind farms, which are the color yellow, have lower coherency, which is consistent with the example we saw before, that closer wind farms have higher coherency, while distant wind farms have less coherency. But you can also see that for all lines, for all square coherence functions, the square coherence decreases with increasing frequency. This is an equation from the literature, where you can see that it tends to decrease exponentially with increasing frequency. So what I want to do with this, I want to see how the general coherence, if we can make an analytical model describing the coherency between the different sites. So all these lines are plotted separately in one panel here, and then each square coherence function is fitted with this equation from the literature. And from each of this panel, I derive A and B from regression, and then I plot it with respect to distance between intersites. You can see there's a clear correlation between the parameter B and the intersite distance, which, yeah. So these three equations, the model and the parameters A and B, are expressions how the wind power coherency in generally acts in the Faroe Islands. So to compare to other results from other studies, you can see here that the red line is the square coherence function based on the analytical model of the Faroe Islands for different intersite distances. And then I've shown 4 examples from the literature and plotted the square coherence function for them also. And you can see that the square coherence function for the Faroe Islands has lower values, the red ones, which means that it's speculated the reason for that is because we have complex topography in the Faroe Islands, which means that the flow has higher, mixes faster with respect to distance compared to other locations which might be less complex. So to sum up what you've seen, the results from the first article, temporal and spatial fluctuations of the wind power in the Faroe Islands have been characterized using outer spectra and the square coherence functions. An analytical square coherence model has been fitted to the various conditions. However, the spatial coherency of the wind power in the Faroe Islands is less compared to some examples from the literature. Yeah. So now I'm going to go to the second article, which is the validation of force-generated wind field in complex terrain. So the goal of the second article is to validate wind simulations over the Faroe Islands. And the motivation is that this data can then be used to analyze sites where you currently do not have any available wind measurements. The simulations were compared to measurements at 3 site locations during the period of the simulation, which was July 16 to June 18. I like to point out that Eie, the north side E, for example, has a met mass located higher up than the elevation of the 4 grid points of the wharf data, which means that the wharf data does not resolve the hill where the met mass in Eie is located up on. Which we will use later. Here are wind roses from the 3 sites. From measurements and wharf data, you can see that the 2 southernmost sides have mostly westerly winds. However, the northern side, side E, is very much influenced by the terrain. And the wharf data has also this function or influence of the terrain, which is positive that it captures that. Here you see some statistical values. First, to the left, you can see the wind profile of the wharf data as a blue line, and the measured wind speed as red crosses. Especially at site E, the wharf data underestimate the wind speed, and it's speculated that the reason for the underestimation of the wind speed at site E is because wharf does not resolve the hill inside E, which means that the speed-up effect that is caused once the flow actually travels on the hill is not captured, which explains why the wharf data has an underestimation. Also, the standard deviation of the wind speed in site E is also less, and it's likely that the reason is because wharf underestimate the wind speed, and lower wind speed is linked to lower standard deviation of the time series. But the correlation coefficient between all time series is very high for all 3 sites. However, if you plotted the correlation coefficient with respect to wind direction, we see that there is a clear minimum in the correlation coefficient at site E once the wind direction comes from 70 degrees. If you look at a close-up map at site E, you see that the terrain is very complex from that direction. The highest mountains in the Faroe Islands are also located approximately from that direction. And again, it's speculated that the reason for the poor estimates at once wind speed is from 70 degrees is because of the lack of the resolution of the terrain in the wharf modeling. We also want to validate the spectral characteristics of the wind speeds. Not only do we want to validate the mean, but also with respect to different frequencies. The solid lines are the wharf data, spectral characteristics for the wharf data, and the dashed lines are from measurements. Site E has, again, underestimation of the spectral characteristics, but that is because spectra and the standard deviation, they are correlated. Spectra is a representation of the variance. Yeah. However, if we look at site H and site S, they are very similar to measurements, but you can still see a little bit of an underestimation, especially at the highest frequencies, which might be because WRF is a simplified version of reality, so it has more smooth values compared to reality. Here, we compare the square coherence function between 2 of the sites. Again, the solid lines are from the WRF data, and dashed lines are from the measurements. You can see that the WRF data has higher square coherence values compared to measurements, which might be because, again, WRF is a simplification of reality. So it might not capture all of the, so it might smoothen out the coherency between different sites. So to sum up results from the second article, hourly WRF-generated wind speeds are validated against measurements, we see that poorer statistical values are absorbed at the more complex areas. The shapes of the spectra and the coherence function resembles those of the measurements. However, the WRF-generated wind speeds are smoother, both temporally, which we saw in the lower tail of the spectra, and spatially, as we saw in the higher square coherence functions. Now I'm going to talk about the results from the third article, optimization of wind farm portfolio to minimize the overall fluctuations, a case study for the Faroe Islands. The results in this study are based on the WRF data, which are, the goal is to optimally place wind farms in the Faroe Islands in order to minimize the 2 to 3 hourly fluctuations of the total time series. And this is important because it reduces the stress on the power grid, especially now that we are planning on integrating a large amount of wind power in the Faroe Islands. It's important to reduce these fluctuations. This map that you can see here has pinpointed some locations, 14 locations around the Faroe Islands, which have previously, in a previous study, found to be favorable wind farm conditions for the Faroe Islands from Magnussen, based on various parameters, wind resource, distance from road, etc. So what I've done is that I have extracted the hourly WRF data at all of these 14 site locations, and using the power curve of a wind turbine, I have modeled hourly wind power data at these 14 locations. All results that are presented now are normalized by the rated power. And because spectra represent time series fluctuations, the objective function in order to optimize the wind farm portfolio is said to be the integral of the spectra from 1/3 hours to 1/2 hours. I like to explain this, the results from this third article by showing example that if we like to choose 3 wind farms in the Faroe Islands, and if we just first place them randomly somewhere, and then we generate the spectra for those 3 wind farms, and if we do the same for all possible combination of 3 wind farms, then we generate the spectra for all of these combinations. Here you see 4 examples, but we do it for all 300 and something examples, and then we extract the spectra which has the lowest values between 1/3 hour and 1/2 hours, and then we reverse the setup and figure out, okay, which combination belong to this spectra. For this case, it's these 3 wind farms that you can see here. And that is the optimized wind farm portfolio with 3 wind farms. But I have to mention here that this is the optimized wind farm portfolio, but the second optimized is almost just as good as the optimized one. So, Here's the same plot, just with a different illustration. So if we do the same calculations, but now instead of extracting the optimized portfolio, we extract the unfavorable portfolio with the highest fluctuations, which in this case, with 3 wind farms, are these 3 combinations. You can see that the optimized portfolio has more distributed wind farms, while the unfavorable portfolio has more clustered wind farms. I want to compare these results differently with. So I generated a time series, an hourly step change time series for the power fluctuations, which tells you how much does the power increase and decrease from hour to hour. And I plotted the probability density function of the hourly step change function, which is basically tells you the hourly power fluctuations. For the red line, which is the optimized portfolio, you can see that at the center, at 0, you have higher values compared to the unfavorable portfolio, which means that for the optimized portfolio, you have more frequent event of 0 increase in the power compared to unfavorable wind farm portfolio. However, at the tail, you can see that the blue line has a higher tail compared to the red line, which means that the blue lines have higher occurrences of larger hourly fluctuations compared to optimized portfolio. I plotted the 5th and 95th percentiles of the hourly step change function. You can see that the red line, or the values for those here. You can see that the red dashed lines are more narrow compared to the blue dashed lines, which means that the hourly fluctuations of the favorable wind farm portfolio fluctuates 90% in between these values, while for the unfavorable conditions, 90% of the time, it has higher, the range is higher for the hourly step change function. Yeah. If we compare the 5th and 95th percentile of the optimized and the unfavorable portfolios, you see that the optimized portfolio has 18% lower 5th and 95th percentiles of the hourly step change functions compared to the unfavorable wind farm combination. Here's another plot, which is a very nice plot where the capacity factor is plotted for all possible combination of 3 wind farms. So there are around 350 dots here. The optimized portfolio, which was to reduce the integral of the spectra of the 2 to 3 hour fluctuations, are the wind farm portfolio connected to the, or the dots further to the left are the optimized portfolio. And you can see that the optimized portfolio have lower 5th and 95th percentiles compared to the unfavorable conditions, which are to the right. As you can see, the colors, the blue and the yellow color represent the capacity factor of the various wind farm portfolios, but there is no correlation between the integral of the spectra and the colors, which means that there is no trade-off between minimizing the 1 to 3 hourly fluctuations and the total power production. But there are variations still in the power capacity, so if you want to choose the best wind farm portfolio, you might not choose the optimal based on the fluctuations. You should also look at the capacity factors, but you can choose the lowest one, the lowest range, and also have high capacity factor at the same time. So if the same calculations are done for, let's say, 7 wind farms here, you again see that optimized portfolio have scattered wind farms, while unfavorable wind farm portfolio have clustered wind farms, the same characteristics as before. And here you see a decrease of 13% for the hourly step change function of the total power production of the optimized portfolio compared to the unfavorable portfolio. So there's a considerable reduction of the power fluctuations. And if you look at the capacity factor, not only for 3 wind farms or 7 wind farms, but for all possible combinations of up to 13 wind farms, you also see here that there's no correlation between the minimization of the 1 to 3 hourly fluctuations and the capacity factor, which is very positive. So to sum up the results from the third article, wind farm portfolio are optimized with the objective to minimize the 2 to 3 hourly fluctuation of the total time series. Hourly fluctuations are observed to be considerably reduced in the optimized portfolios compared to the unfavorable portfolios. The optimized portfolio consists of distance wind farm, while unfavorable portfolio consists of cluster wind farms. And we do not see any trade-off between the minimization of the 1 to 3 hourly fluctuation of the time series and the annual wind energy production. So I'm going to end up with a summary and conclusion of what you have heard. First, the general characteristics of the wind power in the Faroe Islands has been presented. And then we have modeled, that we have validated modeled wind speed that are used in the third study, which optimize wind farm portfolio for the Faroe Islands. One important result from today is that from the third article is that you can optimally distribute wind farms in the Faroe Islands and reduce the amount of 1 to 3 hourly fluctuations considerably, which is very important since we are planning on integrating a lot of power, wind power capacity in the Faroe Islands in the future, without the trade-off of power production. And both of these are very crucial as the reduction of the fluctuation of the time series reduces the stress on the net, and it also reduces the necessary standby equipment that are needed to account for the wind power fluctuations. And the second one is important because you want as much power as possible in order to, for the economics. Yeah, it should not be a trade-off here. So thank you very much for your attention. And you're welcome to read further of the results or the article's source.
Thank you for hello. Thank you for a nice presentation, Turið. I would now like to welcome the third panel, Professor David to the floor. So the floor is yours, David.
Yeah, okay, now you can hear me. Okay, Turið, thank you very much for your presentation today and also for the thesis, which I greatly enjoyed reading. So, as you know, the role for myself and Anna here is to ask you some probing questions about the work. So, I've made some notes of things to ask, which are mainly based on what I would call the written thesis as opposed to the papers, although I, of course, looked at the papers as well. So, the measured data was up to 1 minute frequency, and I think power data was perhaps 10 minutes. So, the measured data would allow a higher spectral resolution. But obviously most of the analysis and the optimization was based on the WRF simulated data, which was hourly. Now, obviously that resulted in a lower spectral resolution, and I just wondered whether it would have been possible to access higher frequency WRF data, or was it that you were limited because the data was provided to you by the company?
The WRF, it's because I didn't make the WRF data myself, right? So I got all of the data from secondhand, and it wasn't even made for me. It was made for SEV, which SEV used in a different, which is the power company of the Faroe Islands, which they use for different purposes. So I just got their data, and that data is hourly data. But the measurements are 10 minutes data also. Yeah.
Okay, so now I wanted to ask about the selection. So for the optimization, which is obviously very important because, as you said, the aim is to make the largest collection of wind power with the least disruption to the power system.
Yes.
So you've chosen to, as you showed very clearly in the presentation, you've looked at the integral, 1/2, 1/3, so frequencies between 2 and 3 hours of variation.
Yeah.
Right. So what I wanted to know is, I realize you're not a power system engineer, but I guess because the whole purpose of the optimization was to minimize the detrimental impact on the power system operation,
Yeah.
I wondered how you could explain then that this 2 to 3 hour timescale was somehow critical for the dynamic characteristics of the existing plant, which are, as you showed, a mixture of hydro and predominantly at the moment diesel.
Yeah.
So why was explain as best you can why you had chosen that particular timescale and how you see that relating to the way in which this conventional plant is operated here on the Faroe Islands.
Yes. So the plants that we currently have here are oil or hydro, and both of them can react faster than an hour. The practical limit was the resolution of the data. So that's why we chose the highest one. But both oil and hydro can react much faster than 1 hour. Takes 15 to half an hour, perhaps, too. Yes.
Right, and I guess if there's two different sorts of timescales associated with the diesels, I guess there's if they need to be started up and synchronized, that's a particular timescale. But if they're operating and they're operating either on set points or under governor action, then they can respond very quickly.
If they're what?
If the diesels are operating, for example, under automatic governing, then they can respond in seconds to changes.
Yeah, but they are not. It's automatic for very high frequency, if I have understood it correctly. But they are manually.
Right. Okay,
yeah.
so that's an important factor then. So the diesels are mainly operated at set points, and these set points are adjusted by the operators on some sort of time basis.
I'm actually not. I don't know the details of the electricity and how it's operated. I just, as far as I know, I just know that the responding time for these power sources are, if you have high fluctuations in other power sources, you need to start a diesel engine, for example. It's not, you don't have to wait more than half an hour or 15 minutes to start it up and to, and it's manually shown.
Okay.
But I'm not that deep into the details of the operation, I must admit that.
Okay,
So, yeah.
that's fine.
Yeah.
Then perhaps for the future work, you might suggest that if people are using WRF data, they could calculate it perhaps at 10-minute intervals rather than hourly to give a bit more resolution at those higher frequencies.
Yes.
They might turn out to be important when there's lots and lots of wind on the power system.
But I can also mention something else, that we use hourly data, right? But if you go to this very high minutes data, right, then you don't expect the coherency to be very high between the wind farms. So an optimal distribution of the wind farms, at least if you have 1 minute data, you don't expect that the wind farm, or I don't expect at least a wind farm 10 kilometers away to be minutely coherent with the other one. So that's also the optimization. There's a link between the coherency of the time series, right? So if you want to optimally distribute wind farms and 1 minute perhaps, right? Then you might just choose the site location with the less fluctuations, all of the power just located at where you have at least minute or second wise less turbulence, right?
Right.
because the coherency is so small.
And then also, and I think you mentioned it explicitly in one of the papers, that of course, even at high frequency, even within a wind farm, there will be turbines in different locations, and at high frequencies, they again won't be perfectly correlated. So you get some free smoothing effect within the wind farms, and perhaps the future wind farms, well, it looks like they'll have more turbines, they'll be bigger. You'll get more automatic smoothing just from the way the wind farms have been built. So that's helpful, isn't
sure.
it?
Then it's wind farm scale. That's true, yes.
Okay. So, one of the papers, which you covered briefly, dealt with seasonal variation.
Yeah.
Right. Now, as you showed, for the Faroes as a whole, most of the sites, actually the monthly means are really much higher in the winter than in the summer. Yeah.
They are.
So I hate to think what conditions are like here for moving around in the winter. But, okay, especially on the high peaks where you get the speed up. So, and obviously then demands for electricity, which weren't specifically part of the thesis, but I'm guessing they will be considerably higher in winter for heating and so on. And so the operational challenges for the power system operators are going to be more pronounced in the winter. So things will be easier in the summer. Okay, less wind but less load and probably less variation in the wind, so operating a power system will be easier, I think, in summer than in winter. So I looked carefully then at both the spectra and the coherence functions to compare how things were in the winter when it's more windy. And so, not surprisingly, because it's more windy, you get more turbulence, so you get higher spectra, especially in the 2 to 3 hour band. So that you'd expect. It wasn't so completely obvious to me, but I would be interested in your explanation. But you also saw in the winter, when the winds are higher, that the coherence was greater.
Yes.
Right. So I just wondered how you, just in very loose terms, how you would explain whether you would expect that to be the case and what sort of process will give the higher coherence. Just like we said, there's higher turbulence because higher wind. What would you say about the coherence function?
I would speculate that the reason for you have higher wind speed, right?
Yeah.
So if you have two sides standing far, so if you have low wind speed, then there is more time for the wind to, this is my speculations, right? More time for the wind to change. But however, if you have high wind speed, it will still go through the same distance, but it has less time to change. Perhaps that can be the reason why there is a higher coherency between, in winter.
I think that's a good suggestion. So, but as you can see, because you put it up, it's really quite a significant effect, isn't it? This so that was comparing, if I remember, the winter with the overall average, I think, or with the different seasons. So it's definitely significant. So maybe then you could argue that perhaps it would be a useful exercise for someone in the future to look at your optimization approach.
Yes.
But focused on the winter data as opposed to the annual average.
Exactly.
You think that would be useful?
I think that is, yes, of course. You should, it makes a lot of sense that you go for the weakest point, kind of, where you need it the most, right? And it makes a lot of sense that you would do that,
Okay, so that's good. I think we're in agreement there. So, then the last one is really just a question about wind power ramps.
Yes.
So certainly I've been involved with researchers in China but they're not the only ones who've been paying a lot of attention to wind power ramps,
Yeah.
because the rate of change of wind power is what the power system operators have to respond to,
Yes.
and is their challenge. So the steeper the ramp, or the more frequent those ramps,
Yeah.
the more challenging to the power system. So I do recognize that you did look at the hourly step changes,
Yes.
and people do as well, look at that, but because ramps, certain plants can respond to certain ramp rates, but not others, ramp analysis has become quite a big thing, and I wondered if you had thought about that yourself, or if you'd done some reading on ramp analysis, or was that why you decided to look at the hourly step changes?
Yeah, I must say I did not think of the ramp analysis per se, but I think that the reason for looking into the hour step changing was a similar concept, just a different method. You don't see perhaps exactly the amount of time it jumps a certain amount in the step change analysis, because but the percentiles have, even though it's not the same measure, it still says that, for example, if here, let me see, if the percentile is 0.12 megawatt per installed megawatt, you know that 10% of the time you will have fluctuations that are higher than that, for example,
Yeah.
right? So I'm admitting that I didn't look at the ramp analysis per se, but the idea is at least connected to that, yeah. So no, yeah.
Okay, and that's fine. And then perhaps one last additional question then.
Yeah.
Wind forecasting, I mean, one of your supervisors from DTU, Gregor Giebel, is a real expert on wind forecasting. The Danes have spent a lot of time on wind forecasting, because obviously the better you can forecast the wind, the more you can anticipate what you need to do with your
Yes.
other generation plant.
Yeah.
So have you any thoughts just generally about forecasting, and perhaps you could tell me if there are plans here in the Faroes for wind forecasting in general, and how geographically specific that might be to the specific sites, just to give me
Yeah.
a feel for where things are moving in the future here.
Yeah, as far as I know, I don't think that there are plans to make forecasts, but it makes sense to do it. Of course, you want to do, you see the weather forecast maybe, but not as far as I know, at least.
Because, I mean, I know that, just from my few days here, that the forecasting of weather in the Faroes is very challenging.
Yes.
So you can
Yeah,
see
yeah.
some forecasts, and then
Yeah.
you come nearer the time and something else is going on.
Yeah, you kind of expect
And things change
that.
very quickly. And I also got the feeling that you can have some good weather somewhere
Yes.
on some of the islands, and then somewhere else something completely different.
Yes.
But I think, yeah, we probably agree then that developing a forecasting capability here for winds in particular would be a very useful thing.
Yes.
To support the
Yeah.
development of and exploitation of wind here on the islands.
Yes.
So thank you very much for your answers. I'm very happy with that. And I think, well, I'll hand over, but I think we now take a short break before Anna delivers her questions. Is that? Ah, right.
Yes. Still not working? Hey. Yeah. Thank you so much, the two of you. We'll have a short break now, 15 minutes, before the last part of the defense, where you can stretch your legs and have some coffee. And if there is anyone in the audience that has a question or two for Turið, you have to report that to me during coffee, and you will be allowed to ask those questions when we start at the last part of the defense. 15 minutes. Thank you. we are ready to proceed. So the audience are ready almost, I can see. So I will hand the initiative to Dr. Anna Estankero. Okay? Yes? So the floor is yours, Anna.
It's working. Is it? Yeah, it's working. Well, first of all, I wanted to thank to the University of Faroe Islands and Professor Hans Georg Beyer for the invitation to be here. And I wanted to congratulate the candidate for her work and for being here defending it. Well, I think as we expressed in the preliminary assessment, we were pleased with the work. We thought it would fulfill the requirements of a PhD dissertation. Nevertheless, I think it's the job of the opponents to have comments and to highlight things that we didn't understand or we thought it could be approached in another way. And have said that, I think I will put you some questions a bit more focused than David, I think, but things that I didn't fully understand or I have doubts about it. I will follow the thesis. If you could please put it. The first part or point that I wanted to clarify is on page 4. And just below the table, you write that the wind power capacity will be 224% of the projected average demand in 2030.
Yes.
How come?
Yeah, this is, how come it's that high, right?
Sorry?
How come it is like more than
100%.
Huh?
How come it is more than 100% of the demand? How do you calculate? First, when we talk about demand,
yes.
normally we think about energy.
Yes.
And what you write there is power being compared, in my understanding, you are comparing power with energy, and to have a stable power system, you need to have the same amount of energy generated and consumed.
Yes.
So that's the figure.
Yes,
strange.
It's a while since I wrote this. If I remember correct, I take this from another article. I think it is 200% of the average, I say demand. So let's say the average production is 40 megawatts now, right? So we want, if that's the average, then we want 40 times 200. That doesn't add up.
Don't worry too much. I think if you are allowed to make small corrections or clarification, this is a minor detail.
Yeah.
But as it is formally not correct in the way it is understood by most of the readers. And that is a warning just. It's strange. It looked strange, but I will not make a big problem out of it. So let's move on. Do not worry about it. And I do have a question about, now I'll pass this question and go to page 13.
13, right?
Yeah. And my question somehow was a hint about it in the preliminary assessment, which is quality control of data.
Yeah.
Because when we look at the description of your work, you didn't handle the mesoscale models yourself.
No.
you also didn't handle the experimental campaigns to the wind resource assessment yourself. So your major work was data handling and processing.
Yeah.
And somehow I thought that you could have showed more what you did in terms of quality control.
Yes.
Especially because quality control has a huge importance in spectral analysis. Spectral methods are very sensitive to problems in data.
Yeah.
And you are so short in the explanation of how did you recover those long periods. How did you do? And
how I did it, yes. Actually, I went through all of the data that I used manually, and I corrected for very obvious errors, like if you have a peak, if you have like extreme wind speed that is not feasible, right? Or if you have constant wind speed, or if of the same wind speed at the same height diverge a lot, then I deleted the obvious errors manually. I went through all of the data manually, and the data I've used, I also look into. I don't use for example, if you remember, I plotted the annual average of the wind power, and then there are gaps. That's because I don't include the data if there's too much missing data. I don't,
you reject those periods.
Yes, and that's also why once I calculated spectra, I used two highs. There were also during the period of the WRF data, right? There are, at the same height, there are maybe 2 anemometers, right? But if there is everywhere, I went through the data manually, and I don't use it if there are too much missing data. I don't remember if it's 10% or 5%, because it doesn't make sense if you have 1 year of data and you only have like half a year, right, of good data. So everything was done manually.
Okay.
And interpolated once I calculated.
Just interpolated.
Once I used it,
Because there are methods that are a bit more sophisticated, and you could have used, for instance, measure, correct, predict MCP methods that are normally used to recover experimental data. And just to be reassured about when you were performing calculating the spectra, power spectral densities, you ensured always that the time series were continuous.
Yes.
Yes, for sure.
But it doesn't mean that you don't have like perhaps 3 data points missing somewhere, or some. You don't have everywhere 100% continuous time series. But if there are too many missing data, I did not use the data.
Yeah. But those points were always recovered with interpolation.
Yes.
Yeah.
Yeah. Except in the first article, I actually used a mixture of if there were 2 heights, measuring 45 meters above height, and then I used data from one anemometers at the same height, both anemometers from the same height.
And you recovered with that.
Yeah. But in the second article, I only used interpolation.
Okay.
Yeah.
Just a curiosity.
Yes.
When you, this is page 14, just after that, when you present the power curve of an Enercon E44,
Yes.
no, 14, 1 4.
Oh, 14, I'm sorry.
It was just the power curve of the Enercon wind turbine you use.
Yeah.
You received that power curve from Enercon, from the Faroese utility?
No, I found it online. The documentation of the different turbines.
Because that is not a power curve according to the IC standards. The downwards part, it's not.
No. Yeah.
It's not a certified power curve, and I was just curious that you had used it.
This is the.
Yeah.
E44.
No, don't worry about it. Don't.
So it is up to. Is it? If you can read it here. So
And
this is the numbers I used.
Yeah.
But The turbines, at least some of the turbines, have this storm control.
They do have storm control.
Yeah, and that's why I included it. And I didn't have the numbers for them, but I included that decrease because they have storm control and because of the explanation in this document where they kind of illustrate
how they do. Yeah.
Yeah, without the numbers though.
Okay, thank you. I was just curious because it's very uncommon to have that, and as a matter of fact, is not a certified procedure, that downward part.
No,
yeah,
exactly. Yes, that's true.
Just in the next page, 15. And this is also a warning because you say that you are going to use Fourier transform, and you put the equation for Fourier transform, and what you have written there for the MATLAB is a fast Fourier transform, and they're not the same thing.
Yay. Yes.
So, do you want to comment on the differences between
fast
Fourier function?
Yeah,
and
so
the
fast
Fourier
Fourier transform, then you have to have something to the power of 2, right? No, yeah, to the power of something, right? The length of the time series.
And it's a numerical procedure of calculation. Is not the elegant equation that you write there.
Huh? It is.
It's a numerical procedure of calculation.
Yeah.
So.
Yeah.
And basically, the fundamental difference is the Fourier transform is a continuous function.
Okay.
And the fast Fourier is a discrete one.
Oh.
Yeah. So.
Yeah.
Maybe
we have discrete. Everything's discrete here.
Maybe you want to put a footnote or something.
Yes. Thank you.
Just on that.
I will do that.
Now. Let's go. This is the part of the thesis that relates to article number 2, and I have to say I enjoyed article number 2 very much. Mm-hmm. Possibly the one I enjoyed to read. I read it very fast because I was enjoying it. Mm-hmm. If you go to page number 30, please. Yeah. Okay. My question is, in your opinion, because you say site H.
Oh, yeah.
Site H, the yellow.
Can I say?
That's not site H, that's
no.
E.
I've noticed this. This is a mistake in the legend.
Yeah. It's E. Now I was calling it wrongly as it is written, but I had already to figure out this is site E. Yeah. But we read your text and analysis, and in your opinion, site E are your worst results.
Yes.
Is that correct?
Yeah.
For me, they are the best.
Oh yes, because you have conclusions, or why?
No, because the most difficult thing to do when you are doing spectral analysis is to ensure that the energy content of each frequency is well divided. So look at the shape of the spectrum that you obtained.
Yeah.
And the with the WRF, and the shape of the spectrum that were obtained out of the experimental results.
Yes.
It's the exact same shape in spectrum.
Yes.
And that is the most difficult thing to do when you're doing spectral analysis.
Okay. Yeah.
And one of the things that I would have suggested you, and maybe if you continue to work in this area in the future, you may do to have an excellent result for site E, is to apply something that is called MOS, Model Output Statistics.
Okay.
Because the error, the deviation you have there is produced by a lack of calibration of your data.
Okay.
So if you had performed model output statistics to WRF, which is common to do in mesoscale modeling of atmospheric resource, they would be in the spot.
Yeah. Okay.
Yeah.
Yeah.
So this is,
Thank you.
I found it very funny.
Yes. Thank you.
And then it comes to, still in this paper, a question that is possibly a bit more difficult to answer, which is, we are looking at B-logarithmic graphics.
What?
Both scales are logarithmic.
Yes. Oh, yeah.
So they seem to be very near, but they are totally far away.
Yes.
As you know.
Yeah.
You look into the data. And we know because we have done that before.
Yes.
Yeah. So your analysis is mostly quantitative. And my question to you is, what do you feel you can extract in practical terms from this analysis and these results?
From the spectral results?
Yeah. To have practical application.
Yes. I would, for the WRF data, comparing to the general, to the measurements, yeah. I think that what I would extract is that you do, I know it's logarithmic though, but the shapes are very similar, as you say, but also I would, the tail are underestimated, so you have smoother WRF data. I think that would be one.
My question was more directed to, you have a plan to increase wind capacity in the Faroes,
yes.
Faroe Islands.
Yeah.
And somehow your thesis may contribute to that plan and to the siting of the wind power plants within Faroe Islands. And somehow what you did is expected to have a practical application in the future.
Yes.
And you didn't quantify the differences. And my question is, how do you feel this work and this methodology was useful in that plan?
The spectral work or the validation?
The spectral outcomes with differences that we know are very large.
I would kind of say the same as before. Like if you want to apply it, the data, you want to validate also the fluctuations in the spectral characteristics, because then you see the different fluctuations in the time series, right? So the output you can have for future from the spectral results might be just the knowledge you have from the differences and the similarities between the WRF data. The WRF data that I validated are also used for the power company SEV. So I think application for reality would be the knowledge you have in the similarity and diversity of the model in general. I don't know if that explains.
It's fair. It's a fair answer. Another question I would just ask you after this one is, didn't you consider to apply a nested microscale model, a computed fluid dynamics, a CFD model?
Nesting microscale model? The thing, I am not a modeler. I could have done it. Like nesting, you mean like...
No, it's just to enter the outcomes of the mesoscale models.
Yes.
As input data.
Yes.
And you have commercial programs. You don't need to program yourself.
No.
There's plenty of them. Wind, Sim, and several others. And you can simulate with great detail a set of islands like in the Faroe. And some years ago, they were difficult to handle, and the results were not that good. But today, you can extract very good results exactly doing as you did, or at least the setup of your work was organized with mesoscale outcomes, and using that wind field produced by the mesoscale outcomes as the input parameter condition for the microscale models. And it would overcome that problem of the grid points that are very far away that you identified.
Yeah.
So that's another suggestion maybe for the future.
Yes.
This is another warning in page 35. I think that gives a...
$35?
35 is that one? No, it's beginning, that's the one. Maybe I was wrong with, no, it's that one. First line, you just say, wind power is an unpredictable power source controlled by the weather.
Yeah.
Well, I question that. Are you sure you want to write that?
It's not unpredictable. It can't be unpredictable. Yes, you can predict it to some extent.
It's difficult to predict.
It's difficult to predict. Yeah.
Call it unpredictable when all over the world there are meteorologists doing forecasts with fairly good results. Not excellent, but fairly good results. Yes. I think it's a too strong phrase, I would say.
Yes, that's true. But it is difficult to, at least...
oh, it is.
Yeah.
Very difficult.
And also the forecasts are erroneous, you know? Like you...
But I would say I would never call it unpredictable.
No.
It's hard, it's difficult to predict, it's difficult to predict with precision. Yes. To accurately predict unpredictable. No, I wouldn't call it. In 2 pages after that, in 37, what it crossed my mind is, and you mentioned that minutes ago, why did you select it 45 meters for your for the height of your time series correction?
Why?
45 meters is the height above ground.
Oh, 45 meters, yes, that's true. The reason why I selected that height was because the current wind turbines in the Faroe Islands have that height. All of them, but the future ones will be higher. That is why I also wrote it in the outline that it would be really interesting to investigate if if other turbine models would react differently, right? But the reason I used 45 was because that's the current, all of the current turbines that are connected to the grid, the height of them.
But you didn't use the power outcome of those turbines in your calculations, or did you? Did you use power time series?
Yes.
Or you calculated them?
This is the, let me see, this is the third study, yeah. I used power output time series.
Yes, somehow I understood you had calculated them using the power curve and the wind speed you had.
Yeah. Now, what was if I use power, model power output. From turbine.
So you model power output. So you could have applied, for instance, what is called the transposition using a power curve or a logarithmic curve, and just put it at the height intended for the modern wind turbines.
I could have done it. Yes,
you could. And if this is to be used as a planning exercise, I would say that probably to have these around 90 meters, or 100 meters, would be more useful for the planning purposes in the Faroe Islands.
Yeah.
This question David already made. And jumping into paper 3, I have a comment here because I tried to figure out how you did it, and couldn't understand really, couldn't find out. You just classify some configurations as good, so we are in paper 3, or the last part of the dissertation. you classify some of the configurations as good portfolios
Yeah.
and other as poor portfolios.
Yeah.
So what I wanted was for you to just synthesize how did you separate the good portfolio from the bad or poor portfolio?
Poor. Yes. So the objective function was this one here, to minimize the spectra of the all different combinations, right? To minimize the spectra. And the good portfolios are those who have the least power fluctuations in the spectra.
So the least below a certain number, or
No, I said good. I have here, right?
so it's better and worse, rather than
yes.
the
So
best.
Oh
and
yeah,
the
yes,
worst,
best
probably.
and worst.
Yeah.
Yes.
Because my doubt is, how do we classify as some are good and some are bad?
Yes.
It's difficult.
Yeah.
Okay.
So the best, yeah.
So the good are the best 3 or 4,
Yeah.
and the poor are the worst
Yeah.
3 or 4.
But I didn't. Also, it's not the one reason I didn't say the best, because the best one with the highest optimization to the left, right? It might have the most optimized value, right? But the second best might be equally good as the best, if you understand. You know
Yes,
what
I
mean?
do. It's not an absolute optimization is not always absolute. So you have similar. Okay, and staying with these graphics, one of the things that I couldn't figure out, and I think it would have enriched your thesis, and you may address that in the future, is it would have been very useful for us as readers of your thesis and trying to analyze the results, to have an information on the cables that connect different islands.
Yes. Yeah.
Because I fear that the southern island wouldn't be connected.
That is true. Yeah.
Okay. So in principle, when you analyze fluctuations, they are only relevant if you have them integrated in the same network.
Yeah, it depends also on future plans. There are talks about building underwater tunnel to the southernmost island. So it depends also on how the future evolves, right? So if we get underwater tunnel, you might get a cable to the southernmost island, and if not. So this optimization assumes that you have the cable, but you could do the exact same without the southernmost island. I've just chose to include it.
Yeah. I would make you a suggestion, which is to do this time-wise or phase-wise, step-wise, saying this is the first step optimum without cables.
Yes.
And this is the second phase optimum because we are going to interconnect this island. And the third with the whole that archipelago interconnected, something like that.
Yes.
It would, in my view, would be more towards a planning exercise rather than a more theoretical one.
Yes. Thank you.
I probably am using all my time by now. Okay, this I made. Let me just check. One of the things that I didn't mention, and that is related to papers, you don't need to go there, it's just a suggestion. Articles 1 and 3 is you could have tried other methods. One of the methods that is giving best results in terms of grouping, clustering of wind parks is a technique called Principal Component Analysis, PCA. Have you read did you read about it?
I remember from school, but I haven't done actual work with it. But yeah, I know what it is.
Yeah,
Or I've heard of it, yeah.
we are using it not only for wind power, but also wind power with PV systems, and it's giving very good results, so you might try to apply it later on. And I have a final question, which I normally do in these situations, which is, if you were starting your dissertation now,
Yes.
what would you do different?
As for the third article, I think your suggestions for different turbine models make sense, might be more applicable. I would maybe try to make the Wharf model myself. If I had time, then I would try also different setups, and I could choose more myself what to the settings. Yeah. I think, yeah.
I'm happy. Thank you.
Thank you.
Yes, we have come now to the end of the defense. So what will happen now is that the assessment committee, they will leave the room, they will relocate to another room, and they will discuss the performance of Turið here in the defense, and they will be back in roughly 10 minutes, and they will provide us with a final evaluation of the defense, and then also the most important thing, and that is a decision on whether the degree as Doctor of Philosophy should be granted to Turið Poulsen. So see you in a bit, and for the rest of you, you can again enjoy the coffee. Hopefully it's still there. No, it's not there. So you can stretch your legs and talk, discuss the exciting work. Okay? Yeah, we are back, or the assessment committee is back, and now the chairman is going to provide the final decision of the assessment.
Hello. Yeah, we have been talking and found that you had a very concise presentation, was elegant. I might actually come and ask you for your PowerPoints, looked really good. You gave a clear and competent defense. You're confident in your work, it's clearly your work and your answers. And you fully fulfilled the expectations of the examiners. Therefore, we are happy to award the title of Ph.D. to you, Turið Poulsen.
So, on behalf of the University of the Faroe Islands, I'm very happy to have been given the opportunity to give you your diploma and to congratulate you. And we were in quite a unique positions that we ended up with two bouquets here. So. So I have decided that you can choose one of them, and the other one will be given to your supervisor. So Hans-Georg, this is for you. Yeah. So congratulations. We have some wine and appetizers for you, so you are welcome to have some food and drinks and celebrate.